In this video, I will talk about if you have f at x equals to x to the power of n, what is f prime at x? So in this case, n is a constant. So n is a constant. So it's not a variable. Okay. Some of you watching this video may already know what the answer is, but it is n times x to the power of n minus 1. So that is the answer. But this video is about the derivation of this derivative. So it's a derivation of derivative. So we are going to derive to this answer here. And I'm going to show you how. Okay, so first of all, to do this, we need the first definition of derivative. So which we know that f prime at x is equal to limit as h approaches 0, f at x plus h minus f at x, all divided by h. So we know that this is the first definition derivative. So in this case, what is f at x here? Well, f at x is x to the power of n. So what is f at x plus h? So we can actually write this as limit as h approaches 0. Now f at x plus h is simply x plus h to the power of n minus, now f at x we know that is x to the power of n given in the question. Now divide by h. So now what can we do? Now we know that if you put 0 into h directly, you are dividing it by 0. That's not the answer we're looking for. So we have to do something. Now first of all, we might have to expand this x plus h to the power of n. So how do we do this? Then we have to actually talk about the Pascal's triangle and the binomial expansion in order to actually expand this x plus h to the power of n. So let's talk about this here. So Pascal's triangle. So what is this? It's easy to memorize because you don't have to memorize. As long as you know addition, you can memorize this. So we start with 1 on the top. The second row is just 1 and 1 on the side. The third row, we start with 1 as well. In the middle is just 1 plus 1 equal to 2, and on this side is 1. Now the fourth row starts as a 1 again. Then in the middle is 1 plus 2 equal to 3, 2 plus 1 equal to 3, and then 1 again on the side. Now the fifth row is also 1, starting with 1, and then 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and on the side is 1 as well. Okay, the sixth row starts with 1 again, like everything starts with 1, and then 1 plus 4 is 5, 4 plus 6 is 10, then 6 plus 4 is 10, and then 4 plus 1 is 5, and then 1 again. Okay, let's do 2 more, I guess. Okay, so 1, start with 1 again. Now 1 plus 5 is 6, 5 plus 10 is 15, and then 10 plus 10 is 20, and then 10 plus 5 is 15, and then 5 plus 1 is 6, and then 1 again on the side. Now one more row. 1, let's start with 1 again, and then 1 plus 6 is 7, 6 plus 15 is 21, 15 plus 20 is 35, and then 20 plus 15 is 35, and then 15 plus 6 is 21, 6 plus 1 is 7, and then 1. Okay, well, let's stop here. It will keep going down. Yes, it will keep going like a pyramid, but we can stop here. So with the Pascal's triangle, what is this binomial expansion? So let's talk about binomial expansion. Binomial expansion. Now, so we are trying to expand like a plus b to the power of n. So what happened here? What do you use? Because these numbers in each row will represent a coefficient of each term after you expand this binomial. Then, just want to talk about this. The first row, right? The first row here is just 1, will represent the power of 0. The second row, 1 and 1, represent the power of 1. The third row, 1, 2, and 1 represent the power of 2. The next row represent the power of 3. And then the next row represent the power of 4. The next row represent the power of 5. Next row represent the power of 6. Next row represent the power of 7. And of course, like I said before, this triangle will continue down, and it will just, the next row will be representing the power of a, and then next row is power of 9. Okay, so let's do an example. Let's use power of 5 here. So power of 5. So we're trying to use this row here. So let's expand this. If this is a plus b to the power of 5. So how do we expand this? Now we have to look at the coefficient here. So we know that the first coefficient here is 1. So we can do 1 times a to the power of n times b to the power of 0. Okay, so next term is, okay, what is the coefficient here? The next coefficient here. We're using this rule, 5. So we have to put 5, a to the power of n minus 1, b to the power of 1. Next term is 10. The coefficient is 10. Okay, so then plus 10, a to the power of n minus 2, b to the power of 2, plus next term. What's the next coefficient? Okay, 10. Yeah, this one. Okay, so 10. Now a times n minus a to the power of n minus 3, and then b to the power of 3, plus next term. The next coefficient will be 5. Okay, so plus 5 plus 5, a to the power of n minus 4, b to the power of 4. Okay, next term, which is the last term. Now it's the power of 1. Sorry, it's a coefficient of 1. Okay, so that will be plus 1, a to the power of n minus 5, b to the power of 5. Okay, so notice here, the coefficient here is just the number in this Pascal's triangle. Whatever row that the power is, then you just need to pick that. Okay, so the coefficient is like that. Then how about the degree of power that I come up with, like the degree of power here, right? This degree of power. So you notice that the degree of power for a, right? The exponent for the term a is n, and n minus 1, n minus 2, n minus 3, n minus 4, n minus 5. So if you have a polynomial that is to a power of 6, then the next one will be a to the power of n minus 6, right? It will be like that. If it's 7, then will be the next term. The next term will be n minus 7. Now, then the exponent for the term b, right, is 0, 1, 2, 3, 4, 5. Oh, 5 is here. So it's 5. As you can see, it's like pattern as well. So if the polynomial has a degree of power of 6, right? Let's say n is equal to 6, then you will have the next term of the next exponent of b will be 6, right? If your degree of power is 7 for this polynomial that you're trying to expand, then the next term will be b to the power of 7. So it's pattern like this. If you are interested in how I come up with this formula, you can check out the video in the link below. Okay, so now in this case, what we are trying to do here is we're trying to expand x plus h to the power of n, which is this one here. But we don't know what n is, so we don't know which coefficient to use either. Like for example, like here. We're using this coefficient because we know n is equal to 5 here, but we don't know what n is, so we don't know which row we should be using. N could be 10, then are we using 10? N could be 20, then we don't know that, right? The coefficient will be totally different for this limit here because we don't know what n is. So in this case, let's just call this coefficient the a term. So this one we call this a1, right? This one we call this a2, call this a3, we call this a4, we call this a5, we call this a6. Now I'm talking about the coefficient, just the coefficient. Okay, so which is the numbers in this? So I'm calling the a term for the numbers in the Pascal triangle here. Okay, so let's look at this by itself. X plus h to the power of n. Let's make sure this looks good. So x plus h to the power of n. So how do you expand this? We don't know what n is, so we have to only write this. We have to write this a1 times x to the power of n times h to the power of 0, right? Just the same as this one here. So the same as this term here, right? So x is a and h is b. Okay, next term, right? a2 times x to the power of n minus 1 times h to the power of 1. So it's the same as this term here. X is a and h is b. So we do this again. So plus a3 times x to the power. Let me make sure that the 3 is actually a subscript 3 after the a. So this is a3 times x to the power of n minus 2 times h to the power of 2. So it's like this term here, the third term, right? A is x and b is h. Okay, so we will keep doing like this. So let's say we'll add, like the next term will be a4, like a4 times x to the power of n minus 3 and then h3 plus, keep going, and then last term. What can we call last term? Now notice that this is the power of 5, right? We're expanding in this example, but the last term is actually a6 here. So if we go back to the Pascal triangle, look at the n here. We notice that when n is 0, it has one coefficient here. When n is equal to 1, we have two coefficient. When n is equal to 2, we have 3 coefficient. So 3 terms. Basically, that means you have 3 terms in the expanded polynomial. That means the number of terms in the expanded polynomial is 1 more than the number of the exponent, the degree of power. So I can, okay, if this is n, then the last coefficient, I would call this plus a. So plus a subscript n plus 1. So it's always like 1 more than the number of terms in the expanded polynomial. Then this one must be x to the power of n minus n times h to the power of n, because that's how it is, right? We know that, okay, if n is 5 here, right, this example here, then n minus 5, right, then we make the a terms to the power of 0, which is 1, make the a term 1 because it's a to the power of 0. Then the b term is actually to the power of the exponent of in the original polynomial. So that's why the last one will be x minus x to the power of n minus n, and then h to the power of n. Okay, so we can write like this. Now let's figure out what the values are here. What is a1? What is a1? Well, we know that a1 is just this row here. It's always like this row. Doesn't matter what n is, a1 is this row. It's always 1. So we can just say a1 is equal to 1. Actually, if you look at this Pascal triangle here, look at the last term, an plus 1, right? A sub of n plus 1. What would be the a sub of n plus 1? Because the last term is always having a coefficient in this row here. And that means it's always equal to 1 as well. So we can also say that that's the same as a sub of n plus 1 is always equal to 1. Okay, but what is a sub 2 equal to? Can we possibly find a pattern, find a formula, find an equation that actually generate this number? What would be a sub 2? A sub 2, you have to look at this row here. This is a sub 2. Okay, so okay, maybe I leave this circle here so that we know what we're looking at. Okay, a sub 2. So there's no, okay, we don't need to look at when n is equal to 0, because n is equal to 0 is just this number here, which is 1. It's not part of the it's not part of the second number, it's not part of the second row. So we can start from the power of 1. So basically here, this one. We can start from here, and then we can talk about all this term here, because it just start from here, right? N is equal to, n is equal to 1. Okay, so let's start with this. When n is equal to 1, then the second term is equal to 1. When n is equal to 2, the second term is equal to 2. When n is equal to 3, the second term is equal to 3. When n is equal to 4, the second term is equal to 4. When n is equal to 5, second term is 5. And when n is equal to 6, the second term is 6. When n is equal to 7, second term is 7. Okay, so now you know that the second term is just the same as the degree of power, the exponent. Okay, so that's okay. We know that a sub 2 is equal to n. We can just say that. Okay, but what is a sub 3 equal to? Then a sub 3 is the third row, which is going to be this row here. This row. It's not as easy as the second row, which is just the coefficient of the second term is always equal to n, which is a degree of power, but the third term is different, because it's like jumping from 1 to 3, that's like 2 increase, and then 3 to 6 is 3 increase, 6 to 10 is 4 increase, 10 to 15 is 5 increase, 15 to 21 is 6 increase. But the degree of power n is just 1 increase on this side, right? It's just increased by 1. So this time, see if we can derive a formula. So we know that when n is equal to, we have to start with n equal to 2 now this time, not n equals to 1, because there is no number for n equals to 1, but it starts with n equals to 2, right? The first term is 1. Okay, so wow, we know that. Okay, when n is equal to 2, a3 is equal to 1. So we can actually write it here. Let's write it here on this side. So when n is equal to 2, a3 is equal to 1. When n is equal to 3, what's a3 equal to? We have to see how the pattern goes. When n is equal to 3, a3 is equal to 3, okay, according to the Pascal's triangle. Now, when n is equal to 4, a3 is equal to, what do we see here? When n is equal to 4, a3 is equal to 6. Okay, so this is 6. When n is equal to 5, a3 is equal to 10. Okay, so 10. When n is equal to 6, what is a3 equal to? a3 is equal to 15. So a3 is equal to 15. So we can do one more. So when n is equal to 7, a3 is equal to 21. So 21. So as you can see, only the third row of the third diagonal row of the Pascal's triangle is circle, because that's what we're looking at right now. And that's because this will be the third term, right? The coefficient of the third term after you expand the polynomial. Okay, so now that's the information we have. What pattern do we have? What is that pattern here? Well, let's start with the first one. Right? We know that, okay, n is equal to 2, a3 is equal to 1. Then we know that in this case, right, n minus 1 give you 1. So we can say that a3, right? This a3, right? It's like that. But is that it? Or can you just do it like this for the second term? Well, if a3, okay, if a3 is 3, if n is 3, then if we put n here, minus 1 is 2. Well, a3 is 3 here, so that's not the case for the second term. How about the third term here, like n equals to 4? Well, a3 is equal to 6, but if you put 4 into this, right, 4 minus 1 is 3. But that's not 6, so that's not giving you the a3 here equal to 6. That means that is not the formula. So there must be something more to this n plus 1. Sorry, there must be something more to this n minus 1. So we know that we can keep this here, n minus 1. But, okay, since this is the first term, we can start with the formula n-1. We're trying to generate an equation here for this. So we can start this n-1, n-1. We can start with this. Okay, let's do a separation here. So this is when n is equal to 2, a3 is equal to 1. Right? This is, yeah. Okay, so what do you do if n is, okay, we put 2 into n minus 1. That is 1. 1 times what equals to 1? 1 times 1 is equal to 1. So you have to actually, let's try using the n again. What can you do? Okay, what can you make? Well, n is 2, but what can you do? Right, divide number gives you 1. Well, I guess that well, if n is 2, so basically 2 divided by, well, k must be 2, so that's equal to 1. So we can say that, okay, so maybe this has to multiply by m over 2. Okay, let's see if that's the formula that can be used for the second term. Now, next term we have to look at when n is equal to 3. When n is equal to 3, well, a3 is equal to 3, if I remember correctly. Yes. Now we know that. Let's start with this again, right? They multiply by, if you put 3 into n, right? When n is equal to 3, you give it 2. 2 times 3. No, actually, 2 times 3 over 2 give you 3. Right, because if you put n, if you put 3 into n, right, it's 2. 2 times 3 over 2 will give you 3. So, how can you make this term equal to 3 over 2, right? Using the n in terms of n. Well, I can always put n over k. So let's say, well, n is 3 in this case, over k give you 3 over 2. Well, we know directly k is equal to 2. So this case, right, is n over 2 again. So we can actually say that, okay, so this time, this is also n over 2. Okay, so far the formula is the same as the first one. So it looks like it's working. Well, let's see, let's do more. When n is equal to 4, a3 is equal to 6, if I remember correctly. Yes, it is. So 6. Okay, now think about this, right? n minus 1. We start with n minus 1 because we know that when you plug 4 into the n minus 1, it's just 3. So 3 times what give you 6? Because we have to make sure that this is equal to a3. Or 3 times 2 is equal to 6. Okay, so what makes you equal to 2, right? If you use it in terms of n. Well, we know that 4 divided by 2 is equal to 2, then that's the same as n over 2 over 2. That's the same as n over 2 because n is equal to 4. So that means, again, this is just, again, multiplied by n over 2. Okay, I will just do one more. If it works, it works. What? N is equal to 5, then a3 is equal to 10. Okay, so a3 is equal to 10. Alright, let's start with n minus 1 times a number. Alright, we know that if we put n equals 5 minus 1 is equal to 4. 4 times what give you 10? Or 10 over 4 would give you 10. This is the same as 5 over 2, right? If you simplify this. Again, right, if you put n in terms of n, right, n is 5. 5 over 2 will give you like 10 over 4. Same thing. So that means, again, if you put n minus 1 multiplied by n over 2 in this case, it also give you a3. It's it just works that way. So it looks like all these formulas are consistent. It's just that formula, n minus 1 times n over 2. So I can say that a3 is equal to n minus 1 times n over 2. So that is the a3 term. To write it in a better way, right? a3 is actually equal to, we can write like this, n times n minus 1 divided by 2. Now that's a3. So we got a3 as this formula here. Okay, so we know a3 here, so I can just write here a3. What's a3 equal to? a3 is equal to n times n minus 1 over 2. Now, do you need to bother with what a4 is here? Actually, you don't. We just need to know one thing. a4 here is just another row of numbers, like this one here. You don't need to worry about what's the equation to generate this number. In this case, to prove that what's the derivative of x to the power of n. Because you see this, right? Each of this term here has an h here. And don't forget, we are dividing by h. in our original limit here. Most of this term will be cancelled out at the end, so you don't need to know exactly what a4 is or any a5 or a sub 6, a sub 7. You don't need to know any of this term. We can still prove this. Okay, so in this case, let's just rewrite this expression in terms of n. Okay, so we know that a1 and a sub of n plus 1 is equal to 1. Then we know a2 is equal to n. And we also know that a sub 3 is n times n minus 1 divided by 2. Then we can rewrite this now. So when I rewrite, I'm just going to replace this, so I can rewrite it like this. So I can write it here. And that is equal to limit as h approaches 0. Right, I'm going to expand x plus h to the power of n. And of course, by doing that, I don't need this anymore because I have already used it to explain and it should be good enough for now. I can erase all of this. Then I need a space to go down and to finish up this proof and this derivation. Okay. So here. As x, okay, as h approaches 0. So we know that the first term is, okay, when you expand x plus h to the power of n, the first term is 1, right? X to the power of n times h to the power of 0, plus the second term, we know that a2 is equal to n. That's why we said n times x to the power of n minus 1 times h to the power of 1. So this is the pattern for the exponent, for the degree of power for x and h. Okay, so next one we said this is a3, and we know this is n times n minus 1 divided by 2, now times x to the power of x minus 2 to, times h to the power of 2. Now, this is pattern n minus 1, n minus 2. And for h is 0, 1, 2. Right? Okay, so we know that we will just keep adding, right? We will add all this and then expand, right? Okay, now, last term of this. Well, let's do the second last term. What is the second last term in this Pascal's triangle here? Our second last term is here. And if you notice, it's the same pattern as this. Right? It's the same as the degree of power. So the last term is also the same as n, right? The coefficient for the second last term is also coefficient n. Now we know that x to the power of, what is the power here in the second last term for x? Now the second last term here, we know that. Now this is like x minus 0. This is like n minus 0 for the x exponent. And looks like this is just n minus 1. Whatever the h exponent is, it's just n minus that exponent right here. See, whatever the h exponent is, then it's just the n minus that exponent for the x. Okay, so that means, but we do know that this must be h. Okay, I need some space here. We know that the h exponent here must be n minus 1 because we know the last one will be n. So then we can say that this is n minus 1, right, for the x exponent. Then plus this one will be 1 because last term is 1. Remember, in that Pascal's triangle, the last term here is in each of this row is 1. Okay, so then will be just n minus n because now this one, h is just n. Now, because the last term to the power is n, like according to the example we did here for using degree of power of 5, then the last term here is actually 5. That is n minus 5, so it's n minus n. And n is just, and that's just equal to the degree of power. Okay. That's fine. Okay, of course, right? We don't forget that we're subtracting x to the power of n, right, from this original limit, the first definition of derivative. So subtract x to the power of n. And of course, all of this divided by h. What we did here is we just expanded. So I will have to show you that. this is the expanded form of the x plus h to the power of n. So it's this part here. Okay, so all divided by h. So I'm gonna write here. So what's next? Okay, so what is this? Okay, what is 1 x to the power of n to, times h to the power of 0? Now 1 times x to the power of n is x to the power of n. Now h to the power of 0 is just 1. So that is just 1 times x to the power of n times 1, which is x to the power of n. So the first term is x to the power of n. And the last term, we subtract x to the power of n here. Right, so this cancel out with each other. Okay, so we know that this and this will cancel out. Okay, so we don't have to worry about this term here. Now next, what else can we simplify? I don't think we can anymore. But the next thing is we definitely can divide by h. Right, so all this term will divide by h. So over here, this term will be gone. Like the h will be gone, like with this. And then this term here, this will become 1, like the power of 1. And then in this term, right, so h here will become, I guess this will be n minus 2. And then this one will be n minus 1. So what does it mean? We can rewrite this here, right, this term here. So this is equal to limit as h approaches 0. Now the first term is gone. Okay, now the second term, the h, it's just to the power of 1 in this case here, this one. So when you divide by h at the bottom, the h term is completely gone. Then we do have a term just n times x to the power of n minus 1, well, times 1, because h and divided by h is just 1. So we don't have to write that. Plus the top here. Okay, so over here, there's still one h here. So I will just add n times n minus 1 divided by 2 times x to the power of n minus 2 times h plus, plus, let's do this here. Let's look at this term here. So this term here. Well, this is n minus 2 for h. So we have to write n times x to the power of n minus 1 times h to the power of n minus 2 plus, now this term here, this is h to the power of n minus 1. So we have to write, okay, 1, we don't have to write 1 again. Honestly, n minus n is 0, so x to the power of 0 is just 1. So 1 times h to the power of n minus 1 is just h to the power of n minus h to the power of n minus 1. Right, the x, okay, the back here, this one is already gone. We don't have to worry about that. Okay, so that's it. So we don't have to write the h at the bottom anymore because the h has been cancelled out with the h on the top. So what does it mean? Now, we can plug 0 into h now because it's not dividing by h anymore. So this is n times x to the power of n minus 1. Since there's no h term, we leave it like this. Plus, like, because as x approaches 0, so we put 0 into h in all the h here now. Now, this x minus 2 times 0 plus, plus n times x to the power of n minus n minus 1. Now, times 0, because we put 0 into h to the power of n minus 2, plus now put 0 to h, right, n minus 1. So we know that this is 0, right? This term times 0 is just 0. And then everything in the middle, we still have an h term, right? All these are just 0 here in the middle. Because they all have an h term here still. What this term here times 0 is 0. So now what is left, right? Well, okay, let me just cross this one out in the middle too. So those one become 0. So nothing is left here. The only term left is just this. So at the end, we got n times x to the power of n minus 1. And don't forget, this is equal to f prime at x because f prime at x I have been carrying it down like this. Equals to this and keep equaling. So this is f prime at x, f prime at x, f prime at x. So that is the derivation of the derivative for, right, for f at x equals to x to the power of n. And you know that f prime at x Let me write better. You know that f prime at x now is equal to n times x to the power of n minus 1. Or let's say you use the y notation. Then let's say y is equal to x to the power of n. Then derivative of y with respect to x is n times x to the power of n minus 1. So you can use this notation, or you can use this notation. So here's the derivation. Hope you enjoyed this video. Don't forget to subscribe to my channel. Thank you.